You go. Yep.
So, next speaker is Seong, and he will speak on generalizing the Norton algebra of a Grassmann graph to the underlying projective geometry.
All right, thank you. Yeah, thanks to the organizers for arranging this conference. And as you see here, I'm from Williams College. I finished my first year as a visiting there. All right, so today I'm going to talk about the Norton algebra of a Grassmann graph and how we would generalize this to the underlying projective geometry. So here's a quick overview. Let me just quickly click this guy. All right, so here's a quick outline of the talk. So the Norton algebra of a graph is a commutative but not necessarily associative algebra that is defined on an eigenspace of the adjacency matrix of gamma. And one example that is commonly known is this thing called the Griess algebra. And I'm not going to go into details of what this is, but then this is related to this thing called a monster graph or like a monster group. It's one of those famous sporadic groups that are out there when we did the, the complete classification of the groups. And this talk is going to be about the Norton algebra of a Grassmann graph. And this is a well-known distance regular graph. I'm going to go over the definitions in just a bit. And this distance regular graph is defined from a projective geometry. And the goal of this talk is to generalize the Norton algebra of a Grassmann graph to the projective geometry that we use to define this graph. All right, so let's go through some preliminaries. So let gamma denote a connected graph that has no loops or multiple edges, vertex set x, and the path length distance function partial. The diameter of a graph is defined as the maximal distance between any two vertices. And for a vertex x, we define the gamma sub I of x to be the set of vertices y such that the distance between x and y is equal to I. And usually we're going to abbreviate gamma sub 1 as just gamma. And we say that gamma is regular with valency kappa whenever the size of gamma x is equal to kappa for all choice of vertex x. All right, now we define what is called a distance regular graph. So we say that a gamma is distance regular whenever for all constants h, I, and j and vertices x and y that are distance h apart, the number of vertices that are I away from x and j away from y depends only on the numbers h, I, and j and not on the specific choices of the x and y. And we're going to denote this cardinality by p, h, I, j. So yeah, sorry for those who are on Zoom, but I guess if I were to use the whiteboard, basically the idea is if we have a vertex x and if we have a vertex y, and if their distance is h, then the number of vertices that are distance I away from x and the distance j away from y, this number right here does not depend on the choice of x and y, and it's going to be a constant. Okay, so that's the definition of a distance regular graph, and from now on, we're going to assume that gamma is distance regular. Okay, now we're going to talk about the adjacency matrix and the adjacency algebra pretty much. Okay, so let mat sub xr denote an R algebra that consists of matrices that have rows and columns indexed by the vertex at x and all entries in R. And for I between 0 and d, we're going to define the matrix A sub I as follows. So for x and y that are vertices, the xy entry of AI is going to be 1 if their distance is I and 0 otherwise. And we call A sub I the adjacency matrix of gamma, and we're going to abbreviate A to mean the usual adjacency matrix, which is just A sub 1. All right, now these matrices, they satisfy the following properties. So A naught is going to be I because it's only going to be the diagonal entries that have entry 1 because we need two vertices to be the same. And then the second point is that if you add all the adjacency matrices up, then you're going to get the all one matrix. And these AIs are symmetric. And also AI times AJ is going to equal AJ times AI. And you can write that as a linear combination of a bunch of AHs, where H goes from 0 to D. Okay, and from that we can actually get a hint that the matrices AI form a basis for a commutative subalgebra of mat XR, and we're going to call that a Bose-Messner algebra of gamma. And the algebra M is actually generated by A. By generated, I mean it can be written as a polynomial of A. Okay, now by the eigenvalues of a graph, we mean the eigenvalues of the adjacency matrix A. And this is a well-known fact about distance regular graph. If gamma is distance regular, then it has d plus 1 distinct real eigenvalues, where that d is the diameter of the graph. And we're going to denote them by theta naught to theta d in a decreasing order. Okay, so now let's talk about the primitive idempotents. So there exist matrices EI that satisfy these properties. So these are some technical stuff, but then basically what these matrices do is you can think of these matrices as a projection onto the eigenspace of the adjacency matrix. So the key takeaway here is that A times EI is equal to EI times A, which is theta I times EI, where theta I is the, I plus 1th largest eigenvalue. Okay, and of course, like we always do, we're going to abbreviate E to mean E sub 1, and we call EI the primitive idempotent of gamma that is associated with the eigenvalue theta I, and it has the name because if we apply EI twice, then we're just projecting twice, and that doesn't really do, that is not that different from just projecting once. Okay, and another fact about the primitive idempotents is that these guys form a basis for the Bose-Messner algebra M. Okay, now we talked about the eigenvalues of a graph. We have this thing called the dual eigenvalues, and how are they defined? So we know that the AIs, they form a basis for the Bose-Messner algebra, and the primitive idempotent E also lies in the Bose-Messner algebra. So we can write E as a linear combination of these AIs, and the coefficients that come along with the AI is going to be the size of X inverse. So this is by definition. Yeah, I didn't decide this, someone else did, and I just follow it. But yeah, so we have the size of X inverse times theta I star, and that's going to be the coefficient in front of AI, and the theta I star is what we're going to call the dual eigenvalues of gamma that is associated with E. Okay, now let's talk about the vector space. So let V denote an R vector space consisting of the column vectors with rows indexed by X and all entries in R. So you can actually think of that as a vector space on which the Bose-Messner algebra or that matrix algebra acts on. And by construction, this vector space V can be written as a direct sum of the EIV. So basically, the vector space V can be split up into the direct sum of eigenspaces, and the EIV is the eigenspace that corresponds to the eigenvalue theta I. And yeah, that's what I mentioned. And yeah, let's introduce one more notation. So for X vertex, let X hat denote a vector in V that has X entry 1 and all of the entries 0. So one thing to note is that the vector space EV is spanned by simply just applying that E to X hat while X runs through all the vertices. And these vectors, as we see, are non-zero, they're mutually distinct, and they're also going to be linearly dependent. The way to see that is that the eigenspace EV actually has a dimension that is 1 less than the number of vertices. So that's why we know that it's going to be linearly dependent. Okay, so now our next goal is to define what is a projective geometry, and from that define what is a Grassmann graph. Okay, so the projective geometry is defined as follows. So let FQ denote a finite field with Q elements. Let N be a positive integer greater than 1. Let cal V denote an n-dimensional vector space over this field FQ. And let the set P consist of the subspaces of V. And the set P is basically what we call a projective geometry. So the set P together with the inclusion partial order is a poset that we call a projective geometry. Okay, now one thing we know about projective geometry as a set of subspaces is we can actually partition that into different ranks based on their dimension. So we have P as a disjoint union of P sub 0, which is going to be the 0-dimensional subspaces, P sub 1, which are going to be the 1-dimensional subspaces, all the way up to P sub n, which is going to be the n-dimensional subspace, which is going to be the vector space V itself, the cal V. So yeah, one remark is that we need to distinguish the cal V and the Roman V that we had originally. So the Roman V is the vector space where the matrix algebra acts on, and this V is just a n-dimensional vector space that we use in order to define a projective geometry and the Grassmann graph that will follow soon. Okay, so we defined a projective geometry, and the Grassmann graph is simply just taking a certain dimension and just taking a slice out of it. That's basically what a Grassmann graph is. So let k denote a positive integer such that k is less than n. The Grassmann graph, which we denote by j sub q and k, has vertex set pk. So it's going to be the set of all k-dimensional subspaces of the projective geometry. And two vertices x and y form an edge whenever their intersection subspace has dimension k minus 1. So I won't go into detail, but for those who have seen Johnson graphs before, it's basically a Q analog of the Johnson graph. Yes.
So the projective geometry is geometric. Right? So
Yes.
say, take a slice. So the vertex set here is one level of the geometric lattice.
Yes.
And then how do you vertices?
Right. So if you have two vertices, then you take their intersection subspace. And if the intersection subspace lies in a piece of k minus 1, so if it's one level lower, yeah, then they're adjacent.
So it's geometry.
Yes.
So one level.
Yeah, exactly. Yeah. And in fact, if you actually go, let's say like I level lower, then the distance in the Grassmann graph is actually I. Yeah, that's the way it works. Okay, yeah, thanks for the question. All right, so yeah, some remarks. The Grassmann graph is known to be distance regular. So from now on, we're going to write gamma to be the Grassmann graph JQ and K. And one fact that we know is that the graph JQ and K and JQ and N minus K are isomorphic. And you can simply just take that by just flipping the projective geometry upside down. Okay, and hence without loss of generality, we're just going to assume that N is greater than or equal to 2K. Now, N equals 2K case is actually somewhat special because by flipping the projective geometry upside down, if N equals 2K, then we have a symmetric case. So that is a special case. So we're going to look at a general case where N is greater than 2K. And yeah, sorry to this case of N equals 2K. I'm not going to talk about that today. Okay, so under this assumption, the diameter of the Grassmann graph is simply just K. Okay, so let's talk about some facts about the Grassmann graph. So here are some notations that we're going to use. We're going to use the notation bracket L to mean Q to the L minus 1 over Q minus 1. And we're going to define basically the Q analog of all the combinatorial things that we see. So the bracket L factorial is going to be the product of bracket L minus 1 all the way down to bracket 2, bracket 1. And like we usually do in the factorial, the bracket 0 factorial is going to be interpreted as 1. And we're going to define what is called a Q binomial coefficient. So L choose M in the Q sense is basically bracket L factorial over bracket M factorial times the bracket L minus M factorial. So you see the analog between this notation here and the usual L choose M. It's just that we're sticking a Q somewhere appropriate. All right, and of course, we're going to interpret the L choose M sub Q as 0 whenever the top is smaller than the bottom or when M is less than 0. Okay, so that is that. All right, and here's some facts about the Grassmann graph. So the valency of gamma is known to have this value Q times K times brackets K times brackets N minus K. And then I list out the eigenvalues of gamma as shown there. And then, okay, now I'm going to say what the dual eigenvalues are. But then before that, I'm going to introduce a notation called psi. And that one's actually going to pop up quite often. So yeah, there's a bit of a technical calculation going on there in order to find psi, but they're going to show up quite often. So this is what we're going to define psi to be. And in view of that, the dual eigenvalues of gamma are given as the bottom there. All right, so here's some facts about the Grassmann graph. Okay, yeah, I apologize. There are a lot of notations, but yeah, more notations. So in a projective geometry, we're going to define what the small omega of U is going to be. So for a subspace U in the projective geometry, we're going to define the small omega of U to be the set of one-dimensional subspaces that are contained in U. Okay, and one thing to note is that if we take the whole vector space cal V, then the omega of that is simply just going to be all the one-dimensional subspaces. Okay, now the capital U is going to be the other way. So what I mean by that is if we grab a subspace U, the capital omega of U is going to be all the vertices, i.e. all the k-dimensional subspaces that contain that subspace U. And if U happens to be, or the dimension of U happens to be bigger than k, then we're going to assume that the omega of that is just empty. Okay, so we defined omega, the small omega and the capital omega. Okay, with these notations, we're going to define what is called a Euclidean representation. So this is all the technical stuff, but then long story short, the Euclidean representation is basically a nice way to represent a graph on an eigenspace. So here's the exact definition, but let me just give you a few examples, both for the sake of time and for the ease of understanding. So one example of a Euclidean representation, again, sorry for the Zoom people, but if you have a hypergraph, then yeah, this is basically Euclidean representation of a hypercube, because if you set the center right here to be the origin, and if you grab all these vertices to be vectors, then it actually satisfies all the conditions right here. So let's see what the conditions are. So rho is going to be the map from the vertices to the vectors in the Euclidean space. And let's see. Okay, so E is a Euclidean space, and it satisfies 1, 2, 3. So the Euclidean space is spanned by all the images of the vertices. That is the case because we have 3D. And it says the inner product, in other words, the angle between the two vectors are going to be only dependent on their distances and not on the choices of x and y. And we see that because the angle between the two vectors, let's say this angle right here, if the two vectors are adjacent, then this angle right here is going to be the same as like this angle right here, for instance, because they're all adjacent, and so on and so forth. And of course, the third case, which is a little hard to verify, but if you take the sum of all the row z's where z is adjacent to x, then that is simply just going to be a scalar multiple of the image of x. Okay, and that theta actually happens to be an eigenvalue of gamma. And this example right here, for the hypercube, I believe this is a Euclidean representation in the eigenspace that corresponds to the second largest eigenvalue. Okay, details left as an exercise for you, I guess. Okay, so here's a definition of a Euclidean representation. And this is how we would construct a Euclidean representation of a Grassmann graph. Sorry, let me just keep track of time. Okay, so what we do is we start with the one-dimensional subspaces, and we map that using this equation right here with the S check. So we're going to use that check for the map that takes us from the projective geometry to the Euclidean space. Okay, so the way it works is we're going to take a linear combination of the sum of x hats, where x's are the vertices that contain S, and the sum of the y's, where y's are the vertices that do not contain S. So we're going to take the linear combination of those two, and that's going to be the image of the one-dimensional subspaces. And then we're going to extend that to the whole projective geometry by simply just taking the sum of S checks, where S is the one-dimensional subspace that is contained in U. So that way we can actually grab all the elements in the projective geometry and slap it onto the Euclidean space. And if you only focus on P sub k, i.e. the vertex set of the Grassmann graph, that actually does form a Euclidean representation of the graph gamma, and this is associated with theta 1, which is the second largest eigenvalue. Okay, and this construction was actually quite important because we can actually see that x hat that we defined a few slides ago is equal to E times x hat. So we grab the x hat, that vector, and then we apply the primitive idempotent E, and that result is exactly the x check. All right, so again, yeah, I'm sorry, I'm just slamming through all the definitions, but so let's talk about stabilizers of P. So we're going to talk about the symmetry of P. So recall that the GLV consists of the FQ invertible maps from V to V, and the action of GLV induces a permutation action on the poset P, and this permutation action preserves dimension and the partial order on P. Okay, now we're going to define what is called a stabilizer of U. So let's stab U denote a subgroup of GLV that consists of the elements that fix U. Okay, and we call this a stabilizer of U, and fix U is going to be the subspace of that eigenspace EV that consists of the vectors that are fixed by every element in that stab U. Okay, and this is one of the things that I discovered in 2024. For any subspace U, okay, so subspace, I mean, for every element in the projective geometry, the subspace fixed U is simply just spanned by U check. Okay, now things get a little more complicated if we have multiple elements in the projective geometry. So if we pick distinct U and V that satisfy certain conditions, then we're going to define stab UV to be the subgroup of GLV that consists of elements that fix both U and V. And the stab UV is going to be called a stabilizer of U and V. And fixed UV is going to be the subspace of the Euclidean space EV that consists of vectors that are fixed by every element in the stat UV. Okay, now in this case, the basis is not as obvious. In the previous case, when we had one element, it was simply just U check. In this case, this is the most general case. If we have two elements in the let's see. Sorry, if we have two elements in, that should be a P. In the projective geometry P, then the fixed UV is spanned by U check, V check, the U intersect V check, and U plus V check. And by intersect and plus, I mean the meet and the join in the geometry lattice that we're looking at. Okay, so we see that fixed UV in the most general case is actually going to have dimension 4. Okay, how does that look in the case of the Grassmann graph? Okay, so if we have a Grassmann graph, and if we fix two vertices x and y, then the following vectors form a basis for, that should be a, sorry, that's a typo, fixed xy, and that is spanned by x check, y check, x intersect y check, and x plus y check. And we're going to call that a geometric basis for fixed xy. Okay, so if we have a certain basis, what us mathematicians like to do is we find another basis and simply just find a transition matrix. So one thing we note about the geometric basis is we actually use the fact from a projective geometry because we have that x intersect y and x plus y. We can only define that using a projective geometry. Now, can we come up with another basis by simply looking at the combinatorics of the graph? So that's what we did, and we're going to define bxy to be the set of vertices that are adjacent to x and that are distanced one further away from x than y is. And cxy is going to be the one that's closer. So again, using a diagram. So if we have a graph, and let's fix a vertex x and y, the set bxy is going to be the set of vertices that are adjacent to x but distanced one further away from y. So these are going to be our bxy's. I should have written cal bxy really. And then the ones that are adjacent to x but one closer to y, these are going to be the ones that are called cxy. Okay, now the Roman bxy is simply just going to be the sum of the vectors z hat, where z is the vertex that belongs to bxy, and cxy is going to be defined similarly. And once we do that, we find another basis for fixed xy, and that's going to be x hat, y hat, x check, y check, and bxy and cxy. Just quickly check time. All right, and we're going to call this a combinatorial basis. And of course, if we have two bases, then the most natural thing to do is just look at their transition matrices, and that's what they look like. I'm not going to go through them in detail. This is a result that was found in 2024. So this is from geometric to combinatorial, and of course, combinatorial to geometric is going to be an inverse of that. All right, so yeah, here was some grind with a lot of facts about the Grassmann graph and then how we embed it into a Euclidean space and so on and so forth. Now we're finally getting into the meat of the talk, which is the Norton algebra. Okay, so before we define the Norton algebra, let me just define this one notation. So we're going to define what is called an entry-wise product. So for mu and nu that are vectors in V, and for a vertex x, the x entry of mu circle nu is going to be the scalar product of the x entries in mu and nu. So basically, it's just like a dot product, but then instead of adding at the end, you just like leave it as a column vector. That's what you do for the entry-wise product. Okay, now we recall the notation x hat, which was 1 in the x space and 0 for the others. We just note that if you take an entry-wise product between x hat and x hat, it's just itself. And for any distinct x and y, if we take the entry-wise product, then it's just going to be 0. Okay, so knowing that, we know we now know how to define a Norton algebra, and it's defined as follows. So it's going to be a vector space EV and the Norton product, which we denote by star. So if we grab two vectors, mu and nu, and if we take a star product, the Norton product between those two, then it's the same as taking the entry-wise product of mu and nu, and then we are slapping that onto the eigenspace that corresponds to E. Okay, so that's what a Norton algebra is, and this Norton algebra turns out to be commutative, but not necessarily associative. And the easiest way to see that is, for instance, if we have, again, going into the technical stuff, but then if you take, like, let's say U hat and V hat, if you take the Norton product and then apply the Norton product with V hat, then that's going to be different from U check star, V check star, V check. So yeah, again, like there's a lot of verification to do, but then yeah, it is a known fact that the Norton algebra is commutative, but not necessarily associative. Okay, so how does this apply to the Grassmann graph? There's actually a well-known result by Terwilliger. Thanks. Yeah, he's my PhD advisor. But yeah, he found this result in 2021, and that applies to all general distance regular graphs. And what I did was simply just plug in the numbers that I know about the Grassmann graph, like the eigenvalues and the dual eigenvalues, and it gives me this result right here. That gives me that the Norton product between x check and y check is a linear combination of the combinatorial basis for fixed xy. So we see that the Norton product is going to lie in that fixed xy, and it was pretty well known how to express this in a combinatorial basis. Now, expressing this in a geometric basis is a new result. So this is what they look like. And of course, all we need to do is just grab the previous result and just apply the transition matrix. That's all we need to do. Okay, now that is not super interesting, but what is interesting is we only looked at x check star y check. How can we generalize this to the overall projective geometry picture? So if we grab u check star v check for any element in P, then what is the Norton product going to look like? And here's some results that have been around in the past. So here's some results about the Norton product between two elements that are in the one-dimensional subspaces. And here's the general version of it. Again, there's like a lot of technical details going on in order to prove this, but basically the theorem says we have u check star v check as a linear combination of u check, v check, the u intersect v check, and the u plus v check. So the geometric basis for fixed uv. And the last results I have is that for a single element u, the subspace fixed u is actually the Norton subalgebra that is generated by u check. And the subspace fixed uv actually happens to be the Norton subalgebra that is generated by u check and v check. So it is not only the case that fixed uv contains the u check, v check, and their Norton product. In fact, these Norton products actually generate the Norton subalgebra within that big EV. All right, but let's see. Okay, yeah, I need to make this quick. But yeah, here's a quick summary. So we discussed the Grassmann graph and the projective geometry. We discussed the Euclidean representation of a graph. And then we looked at what is called a fixed xy. And then we discussed the Norton products. And we finished the discussion with the Norton subalgebra that is generated by u check and v check. And that is the end of my talk. And thank you for your attention.
One quick question. I can ask one.
Yes.
So you can only define Grassmann graph for a projective geometry. What about any matroid? You can define Grassmann graph for any matroid. Any matroid is a substructure of its projective geometry.
Right.
Does it have to be projective geometry?
Well, so the graph, the definition that I see for the Grassmann graph is from a projective geometry. I haven't. I believe so. Yeah, I don't know if there are like any other graphs that are defined from like a from like a higher level. Right. Yeah. Actually, yeah, I'm pretty sure if it comes from a lattice, then like distance regularity should be, well, it has to be a certain lattice, I guess. Like, so this thing called a modular lattice, I think that's what's important in order to, yeah, I believe that is what's important to guarantee distance regularity. So yeah, to that extent, I kind of know, but then yeah, I don't know if you can define Grassmann graph in any other